Hi, good morning, and welcome to the ZP webinar. So we like to do this a couple of times a week, and of recent, because there's been lots more questions, we have tended to go a little bit, let's say, earlier on this. So what I'm going to do is I'll go forward and just say that we like to answer technical questions that have come in during the week, but at the same time, if you're if you look for the ZP Academy, you will find free answers at the ZP Academy in terms of we've got a couple of free courses. We do have collaborations. Now, collaborations is a very general topic, and we tend to do collaborations with universities. We do have in Europe and in the UK. And the reason being is they're actually funded. So, but I'll discuss a collaboration today. I'll also discuss jobs, and I'll also discuss Developer Zone and also the workshops. That said, I'll go forward a little bit faster and just say we do have a couple of free webinars. So what will happen today is I will discuss the Sensi-All platform quite a bit. We have a question on measuring mercury in urine, and I think we could really do this. I don't want to say no problems, but actually quite straightforward for us to be able to do that. And we can also, so I would recommend coming to that webinar. If a link pops up, by the way, I will put the link underneath the video as well. We also have a webinar on food sense. I think food sense is also a good way of demonstrating what an electrochemical IVD or in vitro diagnostic can look like. So question number 1 is about mercury. Question number 2 is about glucose. And question number 3 is wearables, sweat analysis. And I think Sensi-All, again, is a good webinar for that person to attend as well. Just to say, we do have a conference happening in the UK about the commercialization of electrochemical assays. This is in June 2024. And again, I'll put a link here and you can essentially find that webinar. So question number 1, somebody's interested in measuring mercury in urine. So today I'll discuss work that we've done, the academic, I say, precedence that this is actually quite straightforward to do, and also I think that our Kate potentiostat kind of effortlessly translate over to doing what's called the Sensi-All. So really making that available to people who could really benefit from that technology is a much easier, let's say, I don't want to say thing, but much easier to do with our Sensi-All platform. And I suppose in some ways collaboration comes from the fact that when you look at ZP, our entire technology stack is designed with either reproducible sensors, either readily available sensors, hardware that's cloud connected, and hardware that's actually more like consumer grade electronics, and cloud connectivity. So in fact, everything we do is all about getting technologies onto the market. You'll see that appear a few times today. The second question is actually asking about glucose, whether our glucose sensors are, he doesn't use the term or they don't use the term CGM, but they are using continuous monitoring. So all of our glucose sensors are really developed to be CGM, continuous glucose monitoring. How long can that monitoring carry on for? I have given them already some data that says that the sensors have been running for in the screen, in what we have on the internet, or the website I should say, is 125 days. What's the smallest difference in glucose levels? Now, smallest difference is really a resolution. See, the sensor is basically a full, I want to say full analog system. It doesn't mind if you're doing very small iterations of glucose or very large. The enzyme system doesn't care. Resolution comes down to electronics. Now our electronics are, we've got a resolution, I want to say very high. We can measure nano amps worth of current. So the resolution problem is not, let's say, not with us. It's really about your experiment and the system that you set up. So the sensor and the electronics have resolution far beyond what you would require. But things like if you set up a noisy experimental setup, that will give you noise, and that will affect your kind of ability to resolve a very small difference in glucose concentration. What I can do is show you our data today, so maybe that will partly answer the question. What is the volume of sample that is required? Now, you're interested in CGM, continuous glucose monitoring. I suppose if you think about continuous glucose monitoring that takes place on the body, when they put these sensors, I've got a few in the room as well, but I haven't got one. I have to go and grab one. When they put these sensors on the arm here, those sensors are sitting in really small volumes of glucose. I would suggest microliters of volume. When you think about a glucose strip for type 1 diabetics, the volumes on that are about 300 nanoliters. So they do have a very small, volume. And then when I think about, when I'm thinking about our kind of work, then we're typically sort of testing at about 4 microliters. So the quick answer is, you really don't need much volume in order to actually make a measurement. Let me just do something quite quickly over here. Just trying to. I'm just trying to make sure that everything is sorry. Make sure that everything was actually still going through the internet. Okay. So the quick answer to your question is you really don't need large volumes. We would typically sometimes test our sensors maybe at 4 microliters if we were using a microfluidic device. Glucose strips could be something like 300 nanoliters. If you think about CGMs on the human body, they really don't have much volume to work in. They may be just a few microliters. So you don't need much volume in order to make a glucose measurement. Question number 3 was really around about sweat patches. So I will talk about monitoring, let's say, analytes in sweat as well. Let me go forward a little bit quicker. Just to say, obviously at ZP, we do have a whole range of electrochemical sensors. And I will try and remember to link to them, but and also we do have a lot of screen printed electrodes as well. Sort of what I want to say is that the heart of what we're doing at ZP is, we're actually manufacturing things, including screen printed electrodes. So when I talk about our SensiAll platform, it's all built upon a reproducible, for example, screen printed electrodes, and I will also link to these guys as well. So I have a few, whoops, I didn't mean to click the link, but I'll put the links underneath the video at the same time. Something that I will talk about a little bit today, but there's also that webinar in January about the SensiAll platform. One of the questions today really is about measuring in urine. I would definitely be using our Kate potentiostat, which then seamlessly feeds into our SensiAll platform. And to really do a wearable, so doing what I would sort of say IVD, in vitro diagnostics, is a lot easier than trying to do wearables. So I want to say that I'd find it easier to work with people on IVDs. We do a lot of wearables, by the way, but these are definitely large programs that are well funded. So I will mention both these technology stacks today. The second one is more relevant to the person asking about sweat analysis. The first one's more relevant to the person asking about mercury and urine determination. So let me get to question number 1. Somebody wants to measure mercury in urine. It's probably worth saying that we do have a lot of information around this, and I'll put a link here. And it's probably worth saying that, well, in fact, we have done a lot of work looking at heavy metals in samples. Now, I must admit, we haven't done mercury, and I will comment on that in a little bit. I did do some literature looking before answering this question, just to get a sense of this. I did see somebody had done some mercury work on gold. They were using gold nanoparticles. It's fine. The thing I would like to say is, if you can use a bare electrode that, for example, you got from a company like ZP and you didn't have to functionalize, every time you functionalize, you add in essentially a fabrication step, and that is a source of reproducibility. And what I mean, a source of irreproducibility. So one of the biggest problems I would say in screen printed electrodes is lots of people are using screen printed electrodes that kind of come from the R&D community, and they're not actually, or come to the R&D community, they're not actually very reproducible. And that introduces from sample, so from test to test, use a different screen printed electrodes. and they end up being sort of fairly variable, and therefore you don't get reproducible nice results. So we do an ice cream printed electrode, but I'm concerned that when you have to do something like casting of gold nanoparticles, that step that you manually do will enter a reproducibility concern, that, or at least for me it will be. I also saw that somebody had also used copper films as well, so I will touch on that a little bit as well. Again, I know that in academia people like to sort of, add extra functional materials on top of screen printed electrodes. I understand that. I will show you that we're doing copper testing and lead testing on just bare screen printed electrodes. I will comment on that. So in fact, here it is. We have done a lot of, and you'll see some lead data later on as well. We have done it on top of our hypervalue carbon electrodes. So this is one of the electrodes that I've definitely linked to today. So I will just say that, if you can use just blank screen printed electrodes. Now, the person asked for collaboration. I suppose it's worth saying that, ZP, we're fundamentally trying to create a series of technologies that will help people who have an idea, like measuring mercury in urine, can actually take it forward. The screen printed electrodes that I'm showing today, we've really worked in being collaborative by actually getting the cost right down. So we're doing like 300 electrodes for 250 euros, and they're actually really reproducible. That means that people can actually get closer essentially to the market because they have a reproducible electrode. And I'll put a link to that here. So we do have a whole series of electrodes. I think I'll say it a few more times today, but I think the carbon 501, I hope that would work. I genuinely believe that was a good one for you. The hypervalue electrode, we do have copper and lead data on those. And then we do have a gold electrode. Now, the only reason I put that one was as my third recommendation is because I don't want, gold basically is extremely expensive at the moment. It's never going to get cheap. Lots of people use gold electrodes in this kind of biosensor work, but actually I would really not, if you can avoid gold. It's just too expensive. It's going to be very hard to actually commercialize sensors on top of gold electrodes. At ZP, when we're doing the detection of something like mercury, we're often using anodic stripping voltammetry. If you're not familiar with it and want me to go into it in a bit more detail, I can do that in another webinar. But essentially, you have the metal ions. You have a plating step where you enrich those metal on the surface by reducing them. Then after a certain amount of time, you do a linear sweep voltammetry, and the metals essentially reoxidize, and the amount of current passed in that reoxidation or that oxidation is proportional to the original copper concentration in the solution in this case. So it's quite a neat method, and it works pretty well. We've done it, as I say, both with copper, and we've also done it with lead as well, and we've got some nice results. I mean, we're down at the sort of, I think we can see 5 ppm, 5 parts per billion kind of results with lead. So we can get... Now, something what I'm thinking about really is, this person's asking for a collaboration, but what you find out with ZP is everything that we're trying to do is with the goal in mind. And the goal in mind is that for this to really be impactful, this has to get essentially into the hands of real people. So unfortunately, it could be children with, I don't say mercury poisoning, but especially sometimes, I think it's near mines sometimes this is an issue. So we've got a sample, we have a sensor, and I think, the sensor should be really, in the end, be one of our screen printed electrodes. And we have some hardware. The hardware is called SenseIt-All. SenseIt-All is designed to get from your lab, you basically take that hardware and you can start giving it to real people, and they can start testing their the concentration of mercury in the urine. So there's an app. Oh, I didn't link to the app today, but there's on the Google Play Store, there's an app called SenseIt-All from Zimmer Peacock. That app can easily be changed to different assays using what's called QR codes. In fact, in this video, when the scientist was first setting up the app, they put the kind of hardware in there. Then they were sort of choosing what to do, and at one point they will have scanned the QR code. In fact, I think they might be doing that now. So here they go in the video. So that's really good, because that really allows us to, if you come up with a new assay, we can make that new assay essentially work. Let me just check something over here. We can make that new assay work on the Sensi-All platform. Sorry, I just have to keep checking my internet because it's a little bit up and down today, so I apologize for that. The app works with a cloud system called Julie. This is very, for me, it's pretty critical that you understand that even if you come up, even if you do some lab work, you get some raw data, converting that raw data into a meaningful number sort of would have meant once upon a time software development. But actually, Julie will essentially do that for you. So the sensor goes to the hardware. The sample, in this case, is urine, goes onto the sensor. The app runs the hardware. The app gives the data back to Julie, and then you can get a result. But actually, what is happening is we put the raw data onto the cloud, and I will talk about how Julie can actually analyze that raw data in order to convert the raw data into essentially a signal. And the nice thing about having Julie in the mix is that you can see the raw data, even so if you've got somebody at a distance from you, as long as they've got a smartphone running that hardware, the data will actually all go to the cloud, and you can actually check it for quality, make sure everything's working okay. And it also means you can share it with third parties like ZP, so that we can also check that the data is good. So we have something called the Sensi-All platform. It's a piece of hardware. It's really designed for collaboration, but often collaboration with us does mean that we're working with companies that want to get electrochemical assays out onto the market. There is a webinar next January, so please sign up for that. When I was looking at the literature, I did notice that in order to detect mercury, there were people using copper and gold, and I mentioned that earlier on as electrodes. I've got a bit of I'd like the assays to sometimes be as simple as possible. So trying to use it on just a bare electrode is my first bit of collaborative advice, because when at ZP you'll see that when we do a screen printed electrode, we check the batch to make sure that our reproducibility is good, so that we find out that our sort of what's called relative standard deviation is 5 or 6%. So that means that if you build a sensor or you build an assay on top of that, you've intrinsically got a good repeatability thanks to the electrodes. But if you then functionize on top of that again, now you're going to introduce a manual functionalization which will essentially make the reproducibility of the reproducibility worse. But we do have Julie, and I will show how I think Julie would work. So if I was looking at this person's this is an act from an academic paper, and I only use it for educational purposes, by the way. Essentially, if you're running that Sensi-All app, it will send the data to the cloud. And at which point then you can use Julie, you can program Julie to actually look for features in that data. And Julie can do, we can look at, look at the current here, look at the current here, look at the current here. You look for the currents that are most indicative of the analyte of interest. When I look at the paper, what the interesting currents I suspect are between here and here and here and here. So you can also teach Julie to, or program Julie to look at differences. Look at this feature, subtract this feature, look at this feature, subtract this feature. So you can do quite a lot of data analysis. You can also just do simple like area under the curve type as well. So you can either look at current versus concentration. So this peak height, for example, would just be current, and you can do a calibration curve versus concentration. Or you can do area under the curve, which really would just be currents times voltage, would also be proportional to concentration as well. So Julie can really help with that analysis, which is good, because what it does is it reduces the barriers between what you did in the lab and actually turning essentially electrochemical signal into a concentration. It's a cloud system, so you don't have to kind of host it or anything like that. ZP hosts it. It's the same for the other data as well. We can look at it using peak heights, or we can look at it using area under the curve as well. So however your data looks, if you're at least using the Sensi-All platform, or you're actually using Kate Potentiostat, the data goes to the cloud, so people like ZP can actually look at it and advise you. Otherwise, that data is locked away from us. I just put this up just to say, I know when I was looking at the literature, people were talking about using gold electrodes or copper electrodes. We do have some copper electrodes, but I'm looking at the pricing of this and thinking, I can see that, it's not going to be, it's at this moment, it's very hard for us to do a low cost screen printed copper electrode. So I'm a bit reluctant and to go on that route. So I think I'm just sort of saying like the carbon 501 is a good one for you. I think the hypervalue carbon electrode, I've got data to, on that hypervalue carbon electrode to say that's good. The gold electrode has more literature precedence, and I'm not happy with that copper. Not happy is a strong term, but it's a bit expensive, and you can sort of give it a go, but I wouldn't necessarily recommend it. Just to say something about reproducibility. So I'm kind of, when you, if you come to one of our food sense demos, for example, you will find on our food sense demo that there's no calibration. We don't do any calibration, and this is really because we do a lot of testing in our laboratory. So for example, we always reject sheet 1 when we're manufacturing, but sheet 2 here, we're testing it by voltammetry. Sheet 6 here, so we're going through the run testing sheets, making sure that we've got reproducibility. And then we look at different sheets, look at the mean, look at the standard deviation, look at the relative standard deviation, and make sure that this is 10 or less than 10 or less percent, because we know that way then we can use it in our products and actually make the products work. But we also then pass these products on to you, let's say, and we're just checking to make sure that our sensors don't have a fundamental problem with their underlying reproducibility. And that's why I like to recommend that hypervalue carbon to you, the 501 carbon to you, or the gold. But the less one is the gold one. The 2 carbons I like you to try. It's interesting that actually I think you'll be doing this work by anodic sweep voltammetry. This is just cyclovoltammetry. But if we look at signal versus concentration on our screen printed electrodes, we do get really good sort of reproducibility, because the fundamental screen printed electrodes are very reproducible. And that is part of our kind of collaboration mentality at ZP, that we are trying to put the best building blocks in place so that people can genuinely make assays that work, and they can actually roll them out to help the real world, let's say. We do have something called the Kate. Kate is really the same hardware as Sensi-All. So Sensi-All for ZP is a way of getting assays into the hands of real people. But in order to, let's say, operate Kate, operate Sensi-All, there's actually something called the Kate potentiostat. And that's really the same hardware, slightly different software. And that means that if you develop upon Kate, then you can actually get those assays onto Sensi-All very quickly, and then you can start releasing it for people to reuse in the real world. Especially when you're looking at mercury in urine. When you're looking at mercury in urine, I think there's a disease called Minamato's disease, where unfortunately people, die from sort of essentially brain injury induced by the mercury. So it's important that you do get these assays out to real people. Otherwise, it just remains locked away in the lab. I've got a couple of links here, and I will put those links. I will put those links in the video underneath the video as well. So with ZP, what I think will happen is that you will end up using one of our screen printed electrodes. Hopefully you'll end up using initially the Kate potentiostat, but that becomes the Sensi-All quite quickly. I hope that the sample goes onto the sensors, but in this case urine. The app will run the hardware. The app gets the hardware back. The data goes up to the cloud, and at which point then I don't want to say program, but you've trained our cloud how to analyze your data. And in fact, the data then immediately goes back to the app, and they get a result. I'd almost call this kind of, it's rapid development, I would say, because the screen printed electrodes exist, the electronics exist. The Sensi-All app is already on the App Store. We can change the Sensi-All to run different assays by just using QR codes. Julie exists. Julie's been been developed for over 9 years, and Julie will turn your electrochemical data into a concentration, and you will also be able to troubleshoot by sharing it by looking at the raw data yourselves, or also sharing it with people like ZP as well. So we've built this entire technology stack really to answer the question, how do we get academic research into the real world? So the whole philosophy at ZP is, you want to measure somebody's mercury in somebody's urine. You're one of these kind of scientists, engineers, entrepreneurs, somebody who wants to sort of solve the problem. So we've put in the hardware. Well, we've put in some hardware, we put some sensors. You have to get these hardware and actually start testing or developing the methodology on top of the hardware. But the nice thing is, once you've done that, when you're even delivering this to people, the data is always going back to the cloud, so you can actually look at it, and it will therefore allow you to sometimes improve things like the data analysis. So you're kind of in this loop. And what what's unusual about ZP is people come to us obviously looking for electrochemical advice, but what we're also quite good at is actually the kind of commercialization routes, because what I'm describing in some ways of giving product to people, you looking at the data, trying to improve the results, is really a kind of lean startup mentality. So I'd like to describe that I have a sort of minimal viable product mentality. So in summary, here are the screen printed electrodes, the 501 and the hypervalue carbon electrodes. Either one of those will work. It's really a kind of personal choice which one you would like to kind of go for. The Cape potentiostat exists. It's a beautiful device. It's more like an Apple product than a traditional lab potentiostat. That will connect to the Julie cloud. So you really just have to start getting mercury samples and testing them on this technology, looking at the data. Then you can share the data with us, and I can advise you how it's working. So I'm going to change tack slightly now and talk about glucose sensors. The questions again are, can they be used for continuous operation? The quick answer is yes. For example, I can show you data. We've had glucose sensors that we've had for years, but really it also depends on how you use them. But at least in our hands, we can get a good 6 months worth of operation out of a glucose sensor. What's the smallest difference they can measure? The smallest difference in glucose they can measure really depends on your experimental setup. I suppose I'll answer the question today by showing you some of our data. The smallest volumes they can test are, a glucose sensor really only needs about 300 nanoliters of solution to actually detect. We typically test in our lab, if we're just pipetting onto an electrode, sort of 30 to 50 microliters. So the glucose sensor is part of the whole suite of electrodes that we have or biosensors that we have at ZP. This is one of our, this is the data from our, I have it on the website from one of our glucose sensors. And then we do have some data also showing longevity as well. I want to just describe the experiment to generate some of that data. So we take our glucose sensor, we put it in, for example, a stirring beaker like this. We make electrical contact at this end. We turn on essentially turn on the experiment, we get a spiking current and then it relaxes. This is called the charging current. This is not the webinar to discuss that today, but you wait 100 seconds and then you add some glucose in and the signal jumps up. You add some more glucose in and the signal jumps up. You add some more glucose and the signal jumps up. That alone, by the way, demonstrates that this is really a CGM system, because that sensor, if it wasn't a CGM system, the signal would die because all the enzyme was sort of dissolving out into the bulk, but it doesn't because we've actually held the enzyme in place. And then you can add some more glucose. It's probably worth saying that that's 0 millimolar glucose there. That's 5, that's 10, that's 15, that's 20. So you can get a sense of that. Now, if you zoom in there, you can easily resolve, 1 and 2. You may probably even be able to resolve down to 0.1. But the point is that the sensor doesn't care about the glucose concentration. It's an enzymatic system. It's sort of, there is in the end at the heart of chemistry. There's quantification. It's quantized. So you can't just say it's all analog, but you're nowhere near the levels of sort of quantization in chemistry. So if you do your experiments well, you should be able to resolve things like 0.1 millimolar. We can, but we do our experiments really well. But I can't be in your lab to sort of say how good, let's say, your experimentation is. By the way, we do have flow cells for these kind of sensors as well. It wasn't really part of your question, but just as an FYI, we do have flow cells as well. I don't know what the application you have in mind is, but it's the same as the person trying to measure mercury in urine. If you were trying to do a sort of spots test of some sample, we do have this whole platform, which means that you didn't have to leave somebody in this kind of experimental mode. You can actually give them quite a user experience. So, we do have the sensors, we do have the Sense It All app, we do have the GLU cloud. The data can go to the GLU cloud. We can process it on the cloud and turn it into a concentration. And you can also then, if you're using our technology stack, you can also then share the data with ZP, and we can kind of help to, I don't want to say troubleshoot, but have a look at the data as well. I think the philosophy at ZP, again, is the same thing, that if people have applications in mind, we do have hardware that tries to get those technologies into the hands of the people that you really want to get them into the hands of. And then because you can look at the raw data, it allows you to kind of keep on cycling around and actually improving the method files in order to improve the things like accuracy and precision, which we like to do in the math space. By the way, we do have an API, an application program interface, so this allows you to pull data across to other clouds as well. The last point that I'll make, or sort of summary, is we do have the glucose sensors, and we do have the glucose sensors. They are linked to in this webinar. I'll put them underneath the video as well. We do have the Sense It All platform. We do have GLU. So I suppose it's just, and also the Kate potentiostat. Just say we do have a lot of the hardware in place. So I think we're more interested in sort of freeing people up to actually work on applications rather than always being stuck in the science realm. Question number 3. Somebody's looking to understand sweat volume. So I'm not sure if it understands what's in the sweat or understand the volume of sweat. So all I can really describe is what we've done in the past. So at ZP, we do a lot of wearables, wearable programs with ZP. In the end, wearables is one of the hardest things you can do. These kind of programs run, we do a lot of CGM, continuous glucose monitoring. These kind of programs run into the several million when we're actually doing them, because they're quite tough. This is just a little case study that we did once on the analysis of sweat. So we had some sweat sensors. We put the sensors into a sweat patch. So we were able to collect the sweat off the skin. In this particular case, the sensors were our lactate sensors. So the volunteer is kind of on the bike. They're working out hard. Sweat was collected by the sweat patch. It goes onto the sensor. And then we had Bluetooth connection, and we were able to send the data to the, I want to say data collector, but it was a laptop in this particular case. And at the start, there was no lactate, so we had essentially no lactate signal. Then there was perspiration, but they weren't straining. It's very interesting. As soon as they start straining, they actually got, the signal came up really quickly. And there's also this kind of interesting dip in the signal. And apparently the liver, I think, has something called glucagon that it stores. So when you're kind of straining, at one point the lactate production drops, because actually you've got a secondary sort of store of energy called glucagon. But once that runs out, it doesn't last particularly long. Then the lactate signal essentially kicks back in, and it's been quite. I say this is data that I've looked in on the internet as well. And it's interesting to see that other people have also got very similar data to us. So I suppose if I was to summarize this, then we do have the ability to analyze lactate in sweat, sodium, potassium. If it's the volume of sweat itself, then I can see that we actually also have the capability of measuring volume. But we generally do this as part of programs. So question number 1, I spent a lot of time answering this, and I'm sorry that it was a bit, I don't want to say waffly, but I was also trying to keep an eye on making sure the internet stayed up as well. But we do collaborate with people, but we're also trying to kind of lower the barriers for people being able to do this kind of work. So 250 good quality carbon electrodes, €300. The Kate potentiostat is really a piece of hardware that actually can become the actual product. So suddenly, rather than having a potentiostat in a lab, you actually got something that can actually get delivered to real people in the real world. The Kate potentiostat and the Sense It All platform work with GLU. That's a 9-year piece of cloud system. There's a lot of investment gone into that, and that's also available as well. So you can see the kind of our mindsets are about translating science from labs into the real world, and the entire technology stack is set up to do that. With glucose, I'll just read the questions, make sure I did it again. They are designed for continuous measurement. What's the smallest difference in glucose you can measure? I showed you data which is 5, 10, 15, 20. I appreciate you probably want better resolution than that. Even looking at our own data, you can see that you can look at 1, 2, 3, 4, 5, for example, and we could probably go lower. It's just not something that we're regularly doing. But the sensors fundamentally don't care about that sort of resolution. They're just pure analog systems. Apart from my comment about, in the end, there's quantum chemistry at the heart of chemistry, but you're nowhere near the quantum realm. What's the volume of sample required? I did say that glucose strips actually only need 300 nanoliters. We're often doing microfluidic devices which are 4 to 1 microliters. If we're just pipetting on top of those sensors, we generally use either 30 to 50 microliters of sample. That's the nice thing about electrochemistry. It doesn't necessarily require a lot of sample. Somebody wants to make a sweat patch to understand sweat volume. If it's the volume itself, that's one thing. If it's the analytes in the volume, then that's another thing. But I gave you a quick introduction to our lactate system. So with that, I want to say thank you. Apologies, I'm a little hesitant on occasions. I'm just trying to make sure that I was having a few Wi-Fi problems or wireless problems this morning. But otherwise, I hope that was useful. And if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.